Welcome to qnawire.
A very interesting and important question to make because indeed you're comparing a situation when you have A going into B that has an equilibrium constant Kc, and what you're asking is, let's say, according to your textbook, if you add an initial concentration of 1 mole versus an initial concentration of 2 mole per liter, the textbook says that the equilibrium constant needs to stay the same. On the other hand, what you argue is that if you add 2 mole of A, it is the same as saying 2A going to produce 4 times B, which is a sensible reasoning. It sounds that it is correct, but you're missing the fact that whenever we write down our chemical equations, beneath the surface, what we're doing is taking a hint of what is going on in the reaction mechanism. So, for example, over here, what we are saying is that two molecules of A need to react, they need to get together in order to generate four molecules of B. That side is like in the reaction mechanism, we require two molecules of A, and then something is going to happen to those molecules of A that they are going to generate four molecules of B. But the reaction mechanism requires that both molecules of A. So in this case, the value for Kc, as you point out, would be concentration of A squared, concentration of B to the 4 divided by concentration of A squared. Compared to the initial assessment that we said that Kc, in this case, it would be concentration of B squared divided by concentration of A. Let's call the first one Kc1 and the second one we're going to call it Kc2. Remember that this is just the definition for the equilibrium constant whenever we reach equilibrium. Now, what happens here is that Kc2 is going to be equal to Kc1 squared, right? So, the equilibrium constant for this second reaction cannot be the same as the one for the first one. Another way to point this out is like, for example, A, instead of putting A, let's put a molecule. Let's say we have O2, for example. That is going to generate two molecules of O. In the reaction mechanism for this reaction, what we are saying is that a molecule of oxygen is going to split into two atoms of oxygen. They are far away together. Let me put it further away. On the other hand, on the second reaction mechanism, or the second reaction that you propose, what is going underneath the surface is that what you're saying is that two molecules of oxygen need to collide first, somehow get attached, and after some procedure, what is going to happen is that you're going to end up with four molecules of, well, four atoms of oxygen directly. So that's the main difference whenever we write down a chemical equation. If we multiply a chemical reaction by any factor, what is going to happen is that the equilibrium constant is going to go as squared. So essentially what you are doing when you're changing your concentrations is that in your ice table, the initial concentration is going to change. So in this case, it would be minus x plus 2x. So at equilibrium, you would have C0 minus x and 2x. And the initial value for concentration, it really doesn't matter because whenever we write down our equilibrium constant, this is going to be concentration of B squared divided by concentration of A, which in this case would be 4x squared divided by C0 minus x, right? And that value for the equilibrium constant is going to tell us how much of x is going to be produced, how much of the product will be generating according to that constant. So, just as a summary, you cannot simply multiply the chemical reactions by a number because that is going to alter your equilibrium equation. There's also a thermodynamic argument for that, but the first one that I want you to look at is of the reaction mechanism. You're essentially saying that something else is going on. The example that I put for that is this couple of reaction, the first one and the second one, in which the reaction mechanism might be different, so that's why you need to write them like that. And finally, the thermodynamic argument is going to be that the delta G for a reaction under standard condition is related to the equilibrium constant. And whenever you double a reaction, what happens to delta G is that it is going to change. For example, in the same procedure that we have, A going into 2B, the delta G for this reaction would be equal to 2 times the delta G of formation for species B minus the delta G of formation, standard, of A. If you double this reaction, 2 of A going into 4 of B, the delta G for reaction 2 would be 4 times delta G of B minus 2 times delta G of formation of A, which is essentially 2 times the delta G of formation for the first reaction. And as you can see, that change comes with a change of the equilibrium constant. So that is, in general, why those situations are not exactly the same. When we write it down in a simplified form, as we do in most chemical reaction, it seems like it. But just for you to know, there's a chemical reaction mechanism that is beneath what we're writing down in these cases. So depending on which level you're right now, you're going to see more into detail what is going on in terms of thermodynamics and the actual reaction mechanisms that we have.